I'm going to build two lists of numbers that look like they have nothing to do with each other and then claim they fit together perfectly. Watch. Here's the first list. Take the golden ratio, 1.618, and multiply it by 1, then 2, then 3. Each time, chop off everything after the decimal point and keep the whole number. Keep going, and the top comb lands on 1, 3, 4, 6, 8, 9, 11. Notice it already skipped 2, 5, and 7. Second list, same idea, but multiplied by the golden ratio squared, about 2.618. That gives 2, 5, 7, 10, 13. Now look at what the bottom comb caught. 2, 5, 7. Exactly the integers the top comb missed. Let me mesh them together. Every counting number gets caught exactly once. Never twice, never 0 times. Merge the two lists and you count 1, 2, 3, 4, 5 with nothing missing and nothing doubled, forever. That should bother you. Two lists, built by multiplying and rounding, somehow tile the integers with no seam. This looks like a coincidence. It isn't, and the whole thing rests on one line of algebra. Here's the only fact about the golden ratio we'll use. Its square is just itself, plus 1, phi squared equals phi plus 1, and you can see it as a shape. Divide both sides of that by phi squared. The left becomes 1. The right becomes 1 over phi plus 1 over phi squared. So those two fractions add to exactly 1, put numbers on it. 1 over 1.618 is 0.618, 1 over 2.618 is 0.382. They add to 1. That equation is the engine, hold on to it. To prove the tiling, we count. Pick a finish line, some whole number n, and ask how many teeth of each comb have landed before you reach it. Start with the top comb. Its nth tooth sits at phi times n, rounded down. So a tooth lands before the finish line exactly when phi times n is still below n. Rearrange, phi times n below n means n below n over phi. So the number of top comb teeth before n is just how many whole numbers fit below n over phi. And how many whole numbers fit below n over phi? You take n over phi and round down. So the top comb contributes n over phi, rounded down. The bottom comb works the same way, with phi squared in place of phi. Its count before n is n over phi squared, rounded down. So before the finish line, we have two tallies, n over phi rounded down plus n over phi squared rounded down. Together, that's every tooth that has landed so far. Here's where our one equation earns its keep. Ignore the rounding for a second. N over phi plus n over phi squared. Factor out the n. Is n times 1 over phi plus 1 over phi squared. But that bracket is exactly 1. So without the rounding, the two lengths add to n precisely. N over phi plus n over phi squared equals n dead on. Now the catch, and it's the pretty part. Phi is irrational, so n over phi is never a whole number, and neither is n over phi squared. Each is some whole number plus a leftover fraction. The whole number parts are exactly what the rounding keeps. The leftover fractions are exactly what rounding throws away, and we just showed the full pieces add to a whole number, n. If the total is whole, and the whole number parts are whole, the two leftover fractions must add to a whole number too. Each sits between 0 and 1, so their sum can only be 1. So the two rounded down tallies fall exactly 1 short of n over phi, rounded down plus n over phi squared, rounded down equals n minus 1. Every time. Read that plainly. However far out you set the finish line n, the number of teeth that have landed before it is exactly n minus 1. Here's the move that turns a count into the theorem. Push the finish line from n to n plus 1, one step right. The tally goes from n minus 1 to n. It went up by exactly 1. But the only teeth before n plus 1 that weren't before n are the teeth sitting exactly on n. If the count grew by exactly 1, then exactly 1 tooth sits on n. Not 0, or the count wouldn't have moved. Not 2, or it would have jumped by 2. exactly 1, and n was any integer at all. That's the whole theorem. Every positive integer is hit by exactly 1 comb because stepping the finish line forward always adds exactly 1 tooth. The tiling isn't luck, it's forced. Now a pattern you might have half noticed. Line the combs up tooth by tooth. The bottom tooth is always the top tooth plus its own position number. That falls straight out of our one fact. Phi squared is phi plus 1, so phi squared times n is phi times n plus n. Round down, and the plus n comes along untouched because n is already whole. So the bottom comb is just the top comb with each tooth pushed right by its own index. 2 combs, one built from the other, still splitting the integers with no seam. And notice what we actually used, only one thing, 1 over phi plus 1 over phi squared equals 1. The golden ratio was never special. Any two irrationals whose reciprocals add to 1 split the integers the same way. Take r equal to the square root of 2, its partner s comes out near 3.414. Different teeth, same perfect split. The golden ratio is just the prettiest member of an infinite family. This trick has a name, a Beatty sequence, after Samuel Beatty, who posed it in 1926. But the name was never the point. The point is that one equation, phi squared equals phi plus 1, reaches all the way out to infinity and never lets a single integer fall through.